All right, folks, thanks for being here. My name is Dionne. I work at Apple. I work on the standard library there, so libc++, which is the standard library shipped with Clang. And in a past life, I was a crazy template metaprogrammer. And as part of my duties on the C++ standards committee, I'm quite interested in reflection, compile time programming, code generation, metaclasses, these kind of topics. Also like lambdas. And so the goal of this talk here is really to kind of clear up some misconceptions, or rather some confusion about our plans for compile time programming. So I want to give you a bird's eye view of what we expect is going to happen in the future for compile time programming and reflection. That's kind of the goal of the talk. Hopefully, if I succeed, you'll leave this room less confused than you are right now with respect to what we're going to do, in C++20 and beyond. So before we start getting into the nitty-gritty details, I think it's important to ask ourselves, why do we even care about that? Because C++ is already a complex language, and if we're going to solve problems, if we're going to increase the complexity of the language by adding stuff to it, we need to have some good reasons to do that. And for compile time programming, one of the biggest use cases is constant initialization, where we have basically data that we know at compile time. We have information that we know at compile time, and we want to perform some kind of computation on that data and have that computation performed exclusively at compile time, nothing at runtime, right? And then somehow have the compiler store that information for us somewhere in the program such that we can then use it at runtime. So for example, here I'm generating exponentials from 0 to 1,000, and I'm storing that in an array that I can then access at runtime. And there's, if compute exp is constexpr, then in principle there is absolutely nothing happening at runtime for to initialize that array, right? So there's no static initialization. There's nothing happening when the program starts up. It's just hard coded in the data segment, which is what we want. So that's one use case for compile time programming. Another thing is boilerplate reduction. There are many cases in C++ where even to do simple things, we need to tediously repeat patterns like that. I mean, I'm pretty sure everybody has one of these in their code bases. And sometimes they're generated using macros, and sometimes they're just generated by hand, or sometimes you even have like a Python script or something like that generates them, right? We've all seen that. And actually, Clang is full of that kind of stuff where we generate AST nodes and stuff like that. And it's very, very, very annoying to not to be able to rely on the compiler itself, which has this information because the compiler knows the enumerators. It's really annoying the fact that we can't rely on that knowledge. So solving these topics, these problems used to be super nerdy, like even amongst a C++ crowd, which is not, which is quite something to say. But it turns out that recently everybody's on it. Like everybody is producing papers, talking about that. I mean, the direction group even included reflection as one of the major work items for the future revisions of the language, which is quite something. I mean, I never expected that this would happen, but it is a very hot topic right now. And so as a result, it's super exciting. We see a lot of different proposals, but it's also very confusing because not all proposals are. I mean, it's really hard to see how proposals fit, together, and sometimes they don't, and some ideas are good, some ideas are not so good, and it's very difficult. So it's not reasonable to expect that someone with a day job is actually going to keep on top of all of that. So what I'm going to try to do today is put some order in there and try to give you a little bit of a bird's eye view of what's coming and how it fits together, essentially. Because my job is somewhat to do that summary for you guys. And so, what's the plan? Even though this is C++, we do have a plan. first, we're going to try to make almost everything constexpr. Okay? So we want to expand constexpr such that it can, basically anything that you can write in normal C++, you can write in constexpr and run it at compile time. Not everything, but we want to expand the language, constexpr as much as we can to close that gap. So that's like the first step. Then we want to add an API that allows you to speak to the compiler, to query things from the compiler. The compiler has a representation of your program, right? It parses it, does analysis and so on, and so it knows everything about your program. What we want is simply a way to programmatically query the compiler for the information that it already has. Okay? So the first one is just constexpr. The second one is really what we call reflection, right? Is the ability to reflect on your program. And then as a last step is the ability to actually influence the AST, influence your program programmatically, meaning you extract some information, you ask the compiler, give me the list of members of that type, for example, and then using constexpr, you go and maybe modify these members or create new declarations or whatnot, and then you want to be able to go back to the compiler and say, hey, I want to re-inject that basically into my program programmatically. That's kind of the idea. And so we've got features to enable 1, we've got features to enable 2, and we've got features to enable 3, right? And these 3 things are pretty much disjoint. They kind of build on top of each other, but they're, in some way, they're orthogonal. So there's like not one feature that solves all of this, right? And it's really important to keep that in mind. So the first step is expanding constexpr. And so doing that is necessary if we want to have a computationally complete mechanism with complex data structures at compile time, which is what we want, because we want to run non-trivial algorithms. We want to be able to manipulate data and store it in, not only in a stud array. We really want to be able to do that in maybe have a vector, maybe have a map at compile time. So we need to expand constexpr. And so in C++11, constexpr was really, really limited, right? Basically, we only had a single return statement, no mutation, no control flow, really. So we basically turned into functional programmers, for better or worse, and that's what it was, right? In C++14, we unblocked many, many use cases by allowing control flow, for loops, mutation, and things like that inside constexpr. But we're still limited. There's still many things we can't do, right? And I don't have a lot of love for reinterpret cast, but it's still something we can't do there, right? And so we can't allocate, we can't have try catch, we can't throw exceptions, we can't do virtual calls, and there's a bunch of stuff like that we can't do. And it's a problem, especially allocations, because it means that we can't have variable size containers. We're stuck with stud array or stack allocated things, basically. So if I want to implement a keepif algorithm, for example, it's basically standard copyif, right? Which basically takes a range of integers and then keeps everything that satisfies the predicate. Pretty simple. So I might be tempted to just store the results in a vector, right? But I can't do that if my algorithm is to be constexpr, because vector doesn't work, at compile time, basically. It's not the literal type, so the compiler is going to tell me you can't call this function as a constant expression. So we have to use a fixed size array. That's really painful. It is painful because it cannot be resized, which means that for anything where you don't know the final size of your container, you're in a bad place, right? So what I have to do here, I have to have my keepif algorithm receive the end size of the array that I'm going to produce, which means that before I even execute my algorithm, I have to know part of the answer. I have to know how many things am I going to keep, right? And so here, I made the choice to actually just pass it manually. So I basically ran the algorithm in my head. I was like, all right, I'm going to keep 3 things in my array. So I passed it on line 16 here. I passed it to the function. But that does not compose at all, right? So it's really, really hard to actually build complex compile time applications using constexpr today because of this inability to actually resize containers. And so that's why we see, for example, in Ben Dean's talk where he did compile time parsing, I mean, it was really, really, really difficult because you don't know the size of everything beforehand, so you need to basically duplicate all your code and go make sure that you have enough, that you allocate enough size in advance. And so one thing that we're working on is actually making bringing allocation to compile time. So we want to allow new expressions inside constexpr. And we also need to make standard allocator work at compile time, because that is what the standard containers use. And another thing that this paper does is what we call the promotion to static storage, which I'll talk about later. But so the idea basically is to make the following valid. Okay, so if you look on line 3 here, I'm allocating an array. And I don't recommend doing that. You should be using stud vector, but I'm just trying to illustrate. So the idea here is that you can actually allocate a compile time, and on line 13, you can also deallocate a compile time. So what the compiler does there is pretty simple, actually. You have to remember that when you're executing a constexpr function, you're really running inside the compiler. It's an interpreter for the C++ language, actually for a subset of the C++ language, right? And so what happens there is you request memory, and the compiler it's not going to allocate an array of ints, of course, right? It's going to allocate a data structure inside the compiler interpreter that represents an array of ints. And that's what it's going to give back to you, right? So what we're saying basically is we're just expanding the subset of the language that the interpreter that exists inside the compiler, the subset that it supports. We're just expanding that subset. And so once we've got that, and this is going to be in C++20 unless things go really wrong. This is making progress, right, toward inside the committee. And so once we've got that, obviously we should be making standard vector constexpr, right? So let's go and try to do that. The problem is it doesn't work because vector uses try catch for exception to give the exception guarantees, right, in pushback and other functions like that. And so if you try to actually just make vector constexpr, even with the rest of the paper, you realize that it doesn't work. And so it startles all the way down. You go and you allow try-catch blocks inside constexpr, right? And so this is what we're doing. We're also allowing enabling try-catch blocks inside constexpr functions. The idea here is that currently, even if you don't throw, if you have a try-catch block, it's not going to be a constexpr function. If syntactically there's a try-catch block, it can't be a constexpr function. So, so this kind of restriction is quite bad, actually, because it prevents us from, well, in this case, it prevents us from making vector constexpr, but the idea is that sorry. We're not actually making throw statements valid inside constexpr here. So it's not quite as cool as you think. You can't throw. So we're just making try-catch blocks valid, but not throw statements. And so let me explain what happens here. What happens here is on line 14, well, okay, so what happens here is I'm just querying a subrange of an array, and I'm using array.at, and array.at can throw, right, if I reach out of range. So that's why I'm using a try-catch block here. And on line 14, I'm not reaching outside of the range, outside of the bounds, so it's all good, right? On line 15, though, I'm accessing the array outside of the bounds, so I'm throwing. And this is where it fails. It doesn't fail in the try-catch. It actually fails when I throw inside array.at, because I haven't allowed throw expressions inside constexpr. And the reason why we're not doing that right now is because it would require the constexpr evaluator to actually support exception handling properly, which includes like stack unwinding and other things like that. And doing that at compile time is crazy. Like I'm way, way, way too scared of being stabbed in my sleep by a compiler implementer to actually propose that. So instead, what we're doing is we're just saying, okay, you can have a try-catch block, but you can never throw, right? So so if you throw, the expression as a whole is going to be not a constant expression, which means that if you try to initialize a constexpr variable from that, you get a compile time error, which is what you get today, right? So in the future, we can absolutely extend that. I don't think I'm going to be the one writing that paper because, like I said, I'm a little bit scared. But like it is technically possible to allow throwing exceptions and catching them and doing all that kind of stuff. But for now, what we're doing is we're just syntactically allowing try-catch blocks. But there are basically no ups because you can never throw. Does that make sense for everyone? So that way we can, this is like the shortest path towards making vector constexpr, basically. And so if we go back to standard vector, in C++20, this should just work. So you can just have a standard vector inside constexpr. So you can push back, everything's nice. If you get, if pushback throws for some reason, even though there's a try-catch somewhere in there, or even if you try to actually catch it, like catch bad alloc at compile time, it's not going to work, right? You're going to get a hard error. Basically, the compiler is going to say, you can't throw. Make sense? And so one thing that I mentioned but didn't explain is the promotion to static storage, which we also call non-transient allocation for standard, for people that like the core working group. So promotion to static storage essentially is answers a question of what happens when a constexpr object is used at runtime. What happens when it leaks to the runtime context? Okay. So imagine this. Imagine this here, where I have a constexpr vector with a lookup table, which is a lookup table, right? And everything is filled up at compile time. But then I use it at runtime. I use it by accessing, indices, accessing the table at indices that are only known at runtime. So I don't know in advance which parts of my lookup table I'm going to be accessing, okay? And because I don't know that in advance, it means that the compiler somehow has to store the full table in the program, right? It has to be all there because I could be accessing any parts of it at runtime. So we need to make that possible. So how does that work? Well, it's actually pretty simple. There are a couple of rules here. So if a constexpr allocation leaks to the runtime, if you use it basically beyond constexpr, okay? And if the destructor would clean up the allocation, if it were called, right? Because here, the vector, it's a constexpr vector, the destructor is never really called, right? So if running the destructor would actually clean up the allocation, then we promote it to static storage. That's kind of the idea here, okay? So that's actually nothing new if you think about this. Because if I turn this into a std array instead of a std vector, right? I'm already putting that in the data segment. I'm already promoting to static storage today. So this is nothing new. The main difference is that here you have a contiguous chunk of the data segment which represents your array, whereas in the standard vector case, you have a little place in your data segment which is the 3 pointers which point somewhere else in your data segment, right? To a contiguous block of memory that represents the vector. So basically, we're making it possible to serialize a little more complex data structures to the data segment. That's kind of a way to see that. Sure. Can you go to the mic, please?
So if you have the vector, and during runtime, you expand that vector, what?
And you what at runtime?
Expand the vector.
You can, okay, all right. So you can't expand the vector at runtime because it's a constexpr vector. So you cannot call any non-const methods on it. And actually, I'm going to delay questions to the end just because I want to make sure I don't run out of time. But you can note the slide number. So it's a constexpr variable, which means that you can't actually modify it. You cannot call any non-const methods on it, right? So you compute the data structure, and then you burn it into the data segment, and it doesn't change anymore. So but you're free to look up, in the data structure. You're free to use it as you wish. And so one interesting thing here in the way we're wording these changes is that if executing the destructor would not clean up the allocations that are leaking to runtime, then it is not a constant expression. So you get a compiler error, right? Because you're trying to basically assign something that is not a constant expression to a constexpr variable. Take a little minute to think about that. This means that as a corollary, if you can call a function at compile time, it means that it is leak-free for the set of inputs that you provided. This is pretty cool. We're putting Valgrind out of business, right? So you actually have a leak checker inside the compiler that way, which is really cool. I would not, rely on that only, to check your leaks, because you're not actually using systems malloc, and you're running basically inside an interpreter, which is not quite the real thing, but it's still, pretty impressive. And actually, if you have a friend or a coworker that's a compiler engineer, buy them a drink, because this is huge. I mean, the complexity of C++ compilers now is such that we have a leak detector at compile time. That's pretty cool. And so we've got other things that we in the pipeline for constexpr, basically library level additions. And so one of them is standard string, which is quite obvious, right? Once you can allocate, why not have standard string work at compile time? So there are some challenges to that, which I can explain a little bit later. But this is in the pipeline. The paper is half written, so I'm going to try to get this one in for San Diego in a couple of weeks. And so standard string should work at compile time. There's no reason not to, right? And then standard map, unordered map, set and unordered set. Why not, right? Why stop anywhere? Where do we have to stop, right? So, so all these data structures, I don't see any reason why they wouldn't be constexpr friendly, really, with the new allocation changes. Optional variant, everybody likes them, expected, All of these helper classes too, it should be possible to make most of them constexpr. Some of them might use dirty tricks, like reinterpret cast and things like that internally. So we're going to have to be really careful about that. So we still need to survey some of them. But at least for standard string and standard map and set, maybe not the unordered variants, but for map and set, I'm pretty sure we should be able to have them constexpr, maybe by 20 or 23, depending. And the math functions, I know there's a lot of people that want that, because then you could, pre-compute tables that include, that use the math functions. So that would be quite useful. Another thing is standard thread. No, I'm just kidding. That's the way to solve, the compile time problem, right? Just compile, multi-threaded, everything's fine. So the little smiley there is me after getting punched in the face by a compiler implementer. And so honestly, there is almost no limit to what we can do there, I think. It's just about surveying the standard library implementation. So you go there, you look at it, and you're like, all right, what do I need in the language in order to just throw, to spam constexpr everywhere, right? And usually there's not a lot missing. With the few papers that we've added, usually there's not going to be a lot of stuff missing. So if you have your, a personal preference for having something constexpr, just go and produce a paper. I think that if you survey the implementation and you're confident that we can make it happen, and then you can defend your case, I don't see any reason not to do it, really. However, there are some challenges. So if you do survey one of the implementations, which is what I did for vector and string, you run into a few problems like reinterpret cast or any kind of dirty trick like that. For example, we use some dirty tricks when implementing the small string optimization for std string. So we have to work around these things. Sometimes we use built-ins that are not constexpr friendly as well, so we need to work around those. And there are some things we can't do, like raw memory allocation. There's just no way we can do that. So allocating with new is fine because you tell the compiler which type you're allocating. Allocating with malloc is not, because you're not telling the compiler which type you're allocating. And I actually want to pause on that and really, something needs to sink in here. At compile time, we need to catch all the undefined behavior. Okay, it is super important. If the compiler can't catch all the undefined behavior at compile time, it means that it can run, if you can induce the compiler into UB, it means that the result of running the compiler, your compilation, is whatever, right? So you could crash the compiler, but you could also produce an invalid program, or you could produce a program that is valid but doesn't do what you want, right? So at that point, it's super scary. So the compiler has to catch all the UB at compile time. It has to track everything, which is why we have some limitations. So like reinterpret cast and raw memory allocation like that can't, there's almost no way we can do that because the compiler would have to track every single thing you do with the chunk of memory it just handed you to make sure that you're never shooting yourself in the foot, right? Which is very, very difficult. And that's something that scares implementers, a lot. So raw memory allocation, we probably will, it's not clear that we're gonna do it ever. And there's other annotations, if you look at your C++ standard library, there's other annotations like UBSAN or ASAN or things like that that are used. And they're inherently not constexpr friendly, so we need to work around those as well. And so this is where actually PO 595 comes into play. So this paper adds a way to detect whether the current evaluation is a constexpr evaluation, okay? And this is an expert-friendly, I would say even expert-only feature. It looks like a simple feature, but it's not. It's really, really not. It has a lot of pitfalls, but it's really necessary if you want to implement any non-trivial thing, non-trivial standard container at compile time. So what this does, like I said, is basically it allows you to detect whether the current function is being evaluated as part of a consent initializer. And so, for example, if you want to make vector clear constexpr, you run into the problem that we have ASAN annotations and debug mode annotations, like I said earlier, okay? And these annotations are inherently non-constexpr friendly. There's no way, they don't make sense at all at compile time. So we can't execute them. So you have basically three options here. Either you give up and you just say, all right, too bad, vector clear is never gonna be constexpr. Or you remove the annotations, but then you're pessimizing, well, in that case, you're not pessimizing, but you're making your implementation worse, at runtime, which is the case that we almost always care about, right? So we don't wanna, we don't wanna prevent implementations from having nice features just because we need to restrict ourselves to the subset that constexpr support, right? So that's not really good. Or you do what we're about to do, which is you basically switch on whether you're being evaluated at compile time. So it's not pretty, right? It's not great, but this is why I said it's an expert-only feature, where expect your standard library implementer to use that kind of stuff to give you the ability to not care, about whether you're in a constexpr context or not. So in standard vector, if we are in a constant evaluation, then we're just going to skip all these annotations, right? They're not going to be enabled at compile time. And so the way this works is a little bit tricky. So on line 8 here, I call f, right? And then f will call vector v.clear, so vector.clear. And inside vector.clear, there's this isConsent evaluated call being made, right? And the idea is because x is a constexpr variable, the right-hand side has to be a constant initializer. And because of that, because it has to be a constant initializer, the magic function isConsent evaluated is going to return true. And then we're going to skip the ASAN annotations right here, okay? Which means that we're not going to be running anything that is not constexpr friendly. And so the expression as a whole is a constant expression. In the case of line 11, y does not require a constant initializer. I mean, surely the compiler can figure out that all of this stuff is, it sees everything, all this stuff it could be folded. But the core language does not require the right-hand side there to be a constant expression. And because of that, is constant evaluated will return false. And so we're going to have the normal runtime code there. So this is kind of tricky because at first, when I was shown that, I was like, well, f in both cases is called the same way. And I mean, it seems like clearly the compiler should fold both of them. But this is not how is constant evaluated works. So another common problem that we have is that constexpr does not actually require compile time evaluation. So raise your hand if you've run into that situation where you're not quite sure whether it's being done at compile time or not. Yes, right? So it's a very common problem. And it actually extends way beyond just oh, I wish I knew whether it was done at compile time or runtime. Sometimes it's for some things that we want to do with reflection, which I'll get to later, it does not make sense. It would be dangerous if anything leaked to the runtime. I'll explain that later. So what we want to do is have basically a function which is exclusively a compile time function. There can't be any code generated for that function ever. And so we're adding a new keyword, which means please constexpr this, do it, right? It's not a suggestion. It's not, maybe constexpr. It's no, seriously constexpr. And so the way these functions, we call them immediate functions. And the way to think about them is sort of as being a kind of like an hygienic macro, kind of. Basically, when the compiler sees a square of 3 on line 5 here, it just says, all right, that's an immediate function. Let me go and evaluate that right away, right? So it folds everything. It just does constexpr evaluation, and then it evaluates the function right there. There's never, ever any code generated. And actually, if you try to call it with something that is not a constant expression, okay, it's going to say, whoop, this is an immediate function. I can't generate code for that. I can't evaluate that at runtime. That's a hard error. What linkage do these functions have? You can't take their address. They don't exist at runtime at all. They absolutely don't exist at runtime. So this actually has some very nice benefits. I think we expect those to have some very large compile time benefits, right? Because there's no code gen. They're much simpler, right? But they're also more limited. You can't take their address. You can't do that kind of stuff. I'm seeing some support there. This is great. And so to summarize the constexpr changes, so basically what we want to do here is expand constexpr to support more use cases, all right? That's the general trend. And we want to allow persisting data structures to the data segment. And we also want to allow, well, we don't really want to actually, we kind of have to, but we have to make it possible to sometimes say, all right, constexpr is failing me, so I'm just going to say, if I'm running inside constexpr, then do something else, right? So that's also something that we're allowing, even though we don't really like doing that. And then we also allow requiring compile time evaluation using constexpr bang. Not exactly sure that's the keyword that's going to stay, but we'll see. So do you have any questions on kind of this section? Yeah. I'll take just one or two.
So constexpr ! Forces functions to be evaluated at compile time. I wonder why this design choice accepts of an annotation at the call side of the constexpr function to say that it should be evaluated at compile time, right?
So
why would I need to write the functions twice, the same function twice, to give this contract instead of just specifying at the call side that I want this function to be evaluated?
Okay, so if you want to allow a function to be called both at compile time and at runtime, then you have a way of doing that. Use constexpr. That's already what it means, right? This is for functions where you must absolutely evaluate them at compile time. And the reason why there is no annotation at call site is because the compiler needs to know that that kind of function is special, right? And it can't know that if it's not part of the declaration of the function. So we need that specifier to be part of the declaration of the function. Nico, and then I'll keep going.
Yeah, Louis, thank you. I'm a little bit confused because when evaluating the new trait to find out whether this is a compile time issue, you use a runtime if. So it seems that the runtime if is evaluated now at compile time if the content is special, the expression is special inside this. That sounds like a contradiction to me.
This here?
Yeah. Yes.
Okay, actually this is tricky. If you use an if constexpr, you're gonna introduce a bug. This is why I say this is an expert-only feature. If you use if constexpr, suddenly is constant evaluated is used in a place where a constant expression is required. So it's always true, okay? So you need to use a runtime if. Because then the compiler is gonna check, am I, like as a whole, am I part, like basically, is there a root of the evaluation that requires a constant initializer, right? If you do that so for example, if you use is constant evaluated in an if constexpr or to initialize a constexpr variable in that function, or as an array bound or something like that, anywhere where a constant expression is required, it's always true. So that's why I need to use a runtime if. So the way to think about this is like, I might be, like vector clear might be running at runtime, or it might be running at compile time. I don't know. I'm going to use the runtime if here, which might actually be running at runtime, at compile time rather, right? If I'm in a constant expression. And so you just use a normal runtime if. You don't use the if constexpr. Real quick.
So my question is, C++ is already known to be slow to compile, and now we are embedding an interpreter for a managed language that appears to be very similar to C++. So do you foresee any performance impacts on compilation?
Yeah, okay, so this is actually going to improve compilation times tremendously because instead of using template metaprogramming to achieve these goals, we're going to use basically constexpr, which is much better. So template instantiation is a much worse interpreter than the actual constexpr interpreter. I'm going to have to keep going. You can ask the questions at the end.
Okay.
And so now that we have a bunch of stuff to do constexpr computations, we want to be able to speak to the compiler, right? We want to be able to query information from the compiler. And so basically what this means is just extracting information about types. We can already do that, even though we don't often think of it that way. We already have some reflection. We have size of, right? It's not fancy reflection, but it is some kind of reflection. You have a type, and then you query some information about it, right? What's the size? We can also ask for things like the alignment. Since C++11, we have type traits. So you can ask things like, are you an aggregate? Are you a pod? Are you a pointer? Things like that, right? So we do have some level of reflection here already. But we're limited. And the way we're limited specifically is in what kind of answers we can retrieve. We can only ask questions where the answer is basically a primitive type. And if you think about it, the reason is because we don't have a way, before these constexpr improvements, we didn't have a way of representing that. So if somebody came to the committee and said, hey, I want to add a type trait that returns a list of the members of a struct, immediately the question would have been like, all right, I'm interested, but how do you represent it? And before now, we didn't have a really good story for that, right? So obviously, with the changes that we're making to constexpr, this answer is going to be different now. And so let's talk about reflection a little bit. So the reflection TS, and first of all, a TS is a technical specification. The way to think about it is basically a feature branch for the standard. Okay, so we have the main trunk for the standard, which progresses, and then we fork off feature branches, basically, and we work on features, and eventually we merge them if everybody's happy. That's kind of the way to think about this. And so we've been working on a reflection TS for a couple of years, and the purpose of the TS is to figure out what the query API should be. Okay, what should we be able to ask the compiler? We don't want to figure out the specific implementation of that API. We just want to figure out what the API is, not really like the nitty-gritty details of what the implementation is. And because the TS started several years ago when we didn't have any plans to, we didn't know we were going to go the constexpr way, everything is based on top of template metaprogramming for now. And so an example of using the reflection TS here, where I'm extracting members. So I use this new keyword called reflexpr. To extract a type that a meta type that represents basically the type of foo here. Okay, so this meta foo on line 6 here is a magic type that is essentially implemented as a pointer inside the compiler's AST. Okay, so it's basically a pointer to the AST node that represents foo inside the compiler, but it's a magic type. You can't name it really. However, that magic type has some meta functions that can be applied to it. Here, for example, I'm using getDataMembersT, and that returns another magic type. There's a lot of magic here. It returns another magic type, which represents a sequence of meta types representing each member. Okay, so it's a little bit like a tuple under the hood. You can think of it as a tuple basically containing meta information for the members of the struct. And so just like a tuple, I have some meta functions that I can use to extract individual elements. So get element here, I get the first element. And I get back a meta x, which is essentially a meta type representing the first member of foo. And that is not int. That is some magic pointer into the AST that represents the int, that specific int, right? And then I can query that meta type, extract some information, and finally, I can actually get the underlying type that it represents, which is an int, actually. Okay, so that's a little bit how it works. And so if we want to print an enum here, we can do that. It's a little bit tedious because it's template metaprogramming, but it's totally doable. So I'm not going to go into much details here, but basically, I reflect on my color enumeration on line 4, and I get back a magic sequence of enumerators. And then I create some fancy helper lambda using template lambdas here. And what this lambda does is it basically calls another lambda. I said I loved lambda, didn't I? And so it calls another lambda inside with each index in order, right? So I'm using basically I'm calling the lambda inside a fold expression with the comma operator on line 11. And so this expands basically to a bunch of ifs, one after the other. With each, for I starting from 0 to n, where n is the number of enumerators. So I'm spamming ifs, basically. That's what I'm doing here. It's a really fancy way of spamming ifs. And then I call this helper function with the number of enumerators by creating an index sequence, with the right number of enumerators. Okay, so it's a little bit fancy, but it can be done. And so there's a bunch of other features, like you can get the location where a type or an entity was defined. You can get, like I said, the member types, the base classes, and such information. So we're also thinking about adding reflection on functions, like you can get the parameters and the return type and things like that. There's also plans apparently to add reflection on arbitrary expressions, which is cool but scary. So you could, for example, have an expression, and then you say reflexpr of that, and gives you the AST of that expression, and then you can walk and do crazy things. I'm not exactly sure when or whether it's actually going to happen, but I've heard some plans to do that eventually. But for sure, it's not in the MVP. And the important part here is that the syntax is actually not settled yet. So what we plan to do with the reflection TS is rebase it on top of the constexpr syntax. Okay, so what we want to do is, instead of having reflexpr return a type, we want to have it return an object, a constexpr object. That constexpr object under the hood is just the same pointer to the AST node, but it's represented as a constexpr object. And once you have an object, you're good. You can use a normal C++ syntax, which is much better than template metaprogramming. So for example here, I can get the list of data members as a vector, right? I'm using a constructor template argument deduction here so that I don't have to type the type inside my vector. But so I get a vector of my members, and then I can index my vector just like I'm used to. So I get back the meta information for that member, and then I can use normal methods just to query properties about it. So this is like type traits 2.0, right? And then if I actually want to go back to reify, if I want to go back from the constexpr world back into the type system, I need another keyword to do that. So that's why we need to introduce unreflexpr, which is another keyword that brings, basically, that reifies the meta information represented as a constexpr object back into the type system, right? So you lift it down, you pull it down into constexpr, do calculations, and then you lift it up back up into the type system with unreflexpr. So with this syntax, printing an enum becomes much better. You're out of template metaprogramming there, right? So I get the set of enumerators by reflecting on my enumeration, and then I can iterate using a range-based for loop. A little bit of a fancy range-based for loop. I'll explain what this is. And that's it. And so this for ... thing here is not a normal for loop, okay? It's basically a spanning for loop, okay? It spams out, it unrolls itself essentially, okay? And the interesting part is that at each step in each body that gets spammed out can have a different type if you want for the loop variable, which means that you could actually use a tuple in that place. And this is actually quite important to realize that that this is not a normal for loop, because it's closer to template instantiation than it is to actual a normal runtime for loop, because you could have a different type at each step in your for loop. So the status of reflection right now is like I said, that basically we're trying to figure out what the compiler query API should be, right? We're trying to figure out like what happens, for example, when you have a function which is redeclared and you're asking for the parameter names, which ones do you get? These kind of questions, right? Which are very important to get right. But we're not so concerned at this very moment with the exact syntax that we're going to end up with. We expect that we will rebase on top of the constexpr work when it is ready. So don't go crazy if you see the reflection TS and you're like, what is this template metaprogramming syntax? I want none of this, right? We're just making progress at this point, and we will rebase on top of a syntax that makes a little more sense. And the goal again is to write normal-looking C++ code, which runs at compile time efficiently without template instantiations. Actually, this is driven a lot by compiler implementers that are tired of me basically abusing their compiler to do template metaprogramming, right? They want to put me out of business. So that's what the design here is really aimed to produce an efficient model to do compile time evaluation. So now onto code injection. We considered a bunch of alternatives, like raw string injection, programmatic API to kind of bring back to inject basically code back into the compiler's AST, and then we basically settled on something that we call token sequence injection. Okay, what I mean by that here is that you extract information from the compiler using the query API, so we're using reflection essentially. And then you use constexpr to perform calculations, computations, algorithms on, involving that data. And then what you want to do is basically influence the compiler's AST using that, right? The result of these computations. And to do that, like I said, we're settling on token sequence injection. And I'm going to be a huge tease right now. I'm just going to say go to Herb's keynote. I apologize, but I can't steal his thunder. So, I believe he's going to explain that in much more details. Unfortunately, I'm not going to talk about that. I'm also kind of out of time soon. So to wrap up, I'd like to kind of give a bird's eye view of what I think that the timeline is for this stuff. And I want to say this is not a commitment. This is just me saying what I think is going to happen, but I'm being very optimistic. So this is absolutely not a commitment from me or from the committee or from anything else. Just to be clear here, it's just I think it is reasonable to expect that that kind of timeline is going to be respected. We'll see. So I think in C++20 we're going to see more constexpr, right? Because most of the papers that I presented today, actually they're they're pretty advanced in the committee anyway, or some of them have been merged already, and we don't foresee a lot of problems with them. So we think they're going to make it. So I think standard vector, standard string, maybe standard map if we get the time, they're probably going to be constexpr in C++20, hopefully. And the language features that are required to make these containers constexpr as well. So like I said, try-catch, allocations, the promotion to static storage. We've got virtual calls now too. A few things like that, right? And so I think we're going to see those in C++20. It's pretty safe to expect that. Then we might see an experimental reflection facility, which I'm not exactly sure whether it's going to be built on top of the template metaprogramming syntax at that point, or whether it's going to be rebased already. But we might be able to provide that kind of stuff for 20. That's not too sure, but we might. In C++23, however, we should be able to have a proper reflection facility that is based on top of constexpr. Again, not a hard commitment. I'm just expecting, looking at how things are progressing, that we might be able to make it. We'll see. And we might have some code injection mechanism, although that is kind of a little more complicated. Go to Herb's keynote, like I said. This one I'm not sure we're going to land for 23. But for sure, for 23, there is no reason why we couldn't have like a big chunk of the standard library be constexpr. So I think this is going to change the face of C++, really. I mean, this is huge, right? This opens like a lot of possibilities. We can write really cool libraries with that. Imagine like JSON libraries that just spit out JSON without you having to do anything at all. That's super cool, right? Or like serialization, deserialization. All these things are going to be much simpler. We can increase code reuse a lot, I think, right? We can stop writing boilerplate all the time. We can also make interoperating with other languages much easier, right? Imagine what it would look like to generate like Python bindings, for example, using that kind of facility. It would be much easier than it is today. However, it also opens up really nice possibilities for shooting your foot, right? And that's kind of bad. But we're C++ programmers, so we like to think that we have control. And never forget that with great power comes a lot of fun. So anyway, none of this work would be possible without a bunch of people. And this is really just a subset of the people that are working on that. There's a lot of people involved. And we're really like doing our best to bring that kind of facility to you folks. And yeah, I think we can make something good with C++. Thank you. So I'll be taking questions. Please come at the mics.
Will constexpr ! Work on constexpr variables as well as functions? So that you don't have to say inline or define them.
Constexpr variables, like constexpr bang some variable. So we thought about that. There are some pretty nasty difficulties with that having to do with, I think, their linkage. It's not that story is not really easy to figure out. So for now, we're leaving them out. This is covered in the paper actually, but yeah, we've thought about that, and it's just not. It opens up a can of worms. So we're kind of skipping that for now.
Thanks.
So today, in some of the talks, we were recommended to
Can you speak closer to the mic?
make everything const, and everything kind of moves into constexpr. Should we consider making everything const by default and making stuff mutable only when it's needed to be mutable?
Right. So should we switch the default? Well, C++ is the language that gets the default wrong, right? Should we make everything constexpr by default? I don't think so. Constexpr is actually when you say constexpr in front of something, you're putting a barrier on the implementation. You're saying, I will never implement that function or that functionality in a way that can't be evaluated at compile time. So it's actually you're actually stating a contract, which is why I would personally, I think I would oppose to, for example, having constexpr-ness be deduced automatically by the compiler, that kind of stuff, right? Because suddenly you would be promising way more to your users, say if you're writing a library, than you are currently. So I think I think whitelisting things as being, no, this is good at compile time, this is good, this is not, I think is still a good thing, at least for now. We'll see, whether that changes in the future, but I think for now it's safer to go that way. Yep.
I think this will be short then, given the question that was just asked. Kate Gregory earlier mentioned a method of finding correct constness in your code base by adding const to everything and then starting to delete things. Should we now be doing that for constexpr also? I think you're just going to say basically the same thing.
Yeah, I don't think it's a good idea. I think it's better to selectively enable constexpr, but at that point, I honestly, I think that the kind of stuff we do with constexpr today is too limited for us to have a really, really clear, we don't have a lot of experience with what it would be like to take a whole code base and be like, actually, how about I run my whole application at compile time, right? We can't really do that today. So we might get closer to that, and in that case, we'll get some experience and we'll know whether it makes sense to spam constexpr literally everywhere. For now, I think it's much better not to do that. Yep.
Hi, this idea came to mind when you had your slide on challenges with reinterpret cast with the small buffer optimization with string, for a string being constexpr or not. And so would it be reasonable to consider having an overloaded type class set based on if it's constexpr or not, so you could have different behaviors if you're operating with that class in constexpr versus not, versus saying there's only one implementation that can be used in both contexts? Does that make sense?
You mean different?
Because small buffer optimization makes sense for runtime reasons, when you have performance reasons at runtime, versus at maybe a compile time I have different things I want to optimize for.
Yeah, well, so
still have to be the same class, same name, because in a constexpr function that may be used at runtime versus may be used at constexpr, I want to use the same class, same interface, but have different implementation.
Yeah, so actually, this is what we plan on doing for string specific. We're not going to give you a constexpr string. We're just going to give you std string.
Right.
It's just going to work magically in both cases. And the way we're going to do that is we're going to say, oh, I'm being run in a constexpr context. I think this string does not fit in my small buffer optimization. So you just never use the small buffer optimization.
But then what about types I implement? If I wanted a class, my class, and then a constexpr class, my class, and do that all myself, and have it not be inside the compiler for only standard library types?
I don't think that would work because you can't change the type based on whether you are evaluated.
So the question is, what's your opinion of such a proposal? Is that a worthy proposal to at least even consider?
I think I would need to sit down. I think I would need to sit down and talk about this more concretely to really understand what the implications are. That's what I think.
Totally do that.
I think it's not necessarily a bad idea because I can see some uses for it, but I think it would kind of break the model of the C++ type system, basically. So I think it's something worth considering, but yeah.
So related question, but for functions. Same way I can overload a function on const versus non-const. Can't do that with a type, but you
Closer
load
to
on constexpr for a function versus non-constexpr?
Can you repeat that? I missed it.
Can you overload a function for constexpr versus constexpr bang versus non-constexpr bang?
You can't. No,
Okay.
no, you can't. But what you can do, however, like I said, is basically say, oh, am I being evaluated at compile time or not, and then act differently. Although you should try not to do that. You should let me do that.
And for the is constant evaluated, what about in a constexpr constructor that is not used to construct constexpr variables like std mutex. Is constexpr evaluated be?
What about a constexpr constructor that is used to construct a non-constexpr variable? Is that what you said? Yeah, I mean, but that works today, right? You can have a.
But what would the value of the is constant evaluated?
Oh, I see what you mean. It would not be true because what you're initializing is not constexpr.
Okay, thank you.
Hey there. So my question is, when we're talking about doing a lot more computation at compile time as we expand constexpr, do we expect that if we're doing really, really heavy sort of pre-computations and stuff at compile time, do we expect compilers to be able to somehow cache those values in a way that it doesn't really, really slow down our build, test, write cycle?
Yeah, so there's kind of, today this is what happens with instantiation, with template instantiation. Everything's memoized, right? Everything's kind of cached. And that's actually a problem because it means that we use like a lot of memory when we compile. So I think talking to some compiler implementers, actually there's a big, they want to step away from that. They want to be able to discard values after they've used them. So they basically don't want things to live forever in the compiler. So I would say it's actually undesirable to cache everything.
Well, but what I mean isn't in one run. What I mean is like I run my compiler, it does some computations, something else breaks, I fix it, I run it again, and I don't want to do that same big pre-computation that I did the first time because I didn't change any of that, just like with code that I didn't change. Is that something that is reasonable for us to expect?
I see what you mean. This is definitely not something that we have thought about. It's kind of, this question applies to what we're doing today, right? I would say we don't really have a solution for that right now. If this is something you can do, then you could hoist everything into a separate TU, and then you just compile that TU once, right? But obviously, if it's in the header, then you need to redo the whole computation every time, which is true today with constexpr. And I mean, a solution for that would be really cool. I clearly don't have one right now.
Cool, thank you.
Sure.
I'm not sure that I entirely follow the purpose of allowing try-catch within constexpr. If throw generates a compile time error, then that would mean your try-catch is inherently unreachable code, which you would want to discourage, right?
That's exactly the point. The point.
Why allow it?
Because I want to make standard vector pushback work at compile time. So the thing is, I'm fine if there is a hard error, compile time error, if you actually throw something from within your pushback. But for the majority of cases where you're not going to throw anything, I want it to be a valid constant expression. So as of this paper, basically try-catch is equivalent to just a brace, right? Just you're entering a scope, that's what you're doing. Because it's impossible to get into the catch block anyway. It's kind of a no-up. Does that answer your question?
Well, yeah, I mean, my point is because it's a no-up, then why not just take out the try-catch? What's the point of having it at all?
Oh, okay, right, because it might not be a no-up at runtime.
Okay. Oh, because the second proposal is not included yet.
Well, because if you call that constexpr function at runtime, which you can, and then you run out of memory, you want the bad alloc or you want the out of bounds error, for example, to be
okay.
thrown.
Okay. So then, if you add the second proposal to make a decision based on whether you're running as constexpr or not, then you could actually change. You could actually have the logic in one case and not in the other.
I'm not sure I followed that.
Within the implementation then of the standard vector, if later you add the ability to say, hey, am I running within constexpr, you could then choose to remove the logic in the constexpr case and not even bother with the...
Right, yeah.
Okay.
Yep.
For the modules, for the C++ modules, do you expect actually constexpr expressions to be evaluated when module is compiled or when interface is imported by another module?
That's a good question. That's a really good question. I believe it would be when the module is compiled. Let me come back to you on that.
So I'm going to ask something about the injection part, even though you're probably going to slap my face all the way up to the next keynote. So you mentioned over there, some options, and we seem to be going with tokens.
What?
For injection.
Yeah.
I don't know. The first thought that came to my mind is, wouldn't like something like unreflexpr.
Can you speak closer
right?
to the mic, please?
What?
Can you speak closer to the mic? It's really hard to hear from.
For injection.
Yeah.
Wouldn't like something like unreflexpr be the natural way to do it? Same as you can take real types and functions and whatnot into a representation of an object, taken just the other way.
The problem of code injection is actually quite tricky because you have to generate new declarations and then somehow find a way to inject them into an existing declaration. So unreflexpr is not sufficient for that.
Okay.
So with all of this compile time code, how do I debug it?
Right, big question. How do you debug that? You run it at runtime? I don't know. I mean, yeah. Honestly, I think the tooling for C++ is going to have to kind of follow these changes. It's kind of the same answer as for when Herb is asked questions about metaclasses, for example. We're adding new stuff to the language, and we have to be responsible, but also the tooling has to follow. So I mean, there are some tools that allow you to, for example, step through template instantiation. One of them is called template. So I think it's about tooling there, really.
Yeah.
Yeah.
In the case of the constexpr new,
can you speak closer?
In the case of constexpr new, what does the delete do? Is it a no-op, or does it actually do something in the compiler?
In the case of constexpr, what?
Constexpr new, like memory allocation in constexpr, which you need to make.
It actually allocates memory, like the compiler is actually going to allocate memory for you.
For delete, does it actually delete the memory, or is it a no-op, or?
That's going to depend on your compiler implementation. I expect some compilers might say, I'm not even deleting stuff because I'm just going to free all my pool of memory when I shut down. Yeah. But some other compilers might decide to actually free the memory.
So could you potentially, would array be able to do the same thing in place of the new? So you could just use an array.
In place new?
Instead of a new. Instead of using a new.
What? Yeah.
Could use array, because an array is just allocating memory. It's usually on the stack at runtime, but.
The problem is, the problem is you can't use, you can't allocate memory like that. You can't, the one thing we want to avoid, like I said earlier, is to give you the ability to shoot yourself in the foot in terms of like, oh, I allocate for that type, but I'm in place newing with a different type, that kind of stuff. This can't happen. I think I'm going to have to cut it here because the next session is, we can talk offline after.
Just follow up the previous question that was made here. Is there any proposal for ability to have, I don't know, emit warnings or a way to actually get output of the constexpr?
I'm sorry, I can't hear you. It's really hard.
Is there any proposal for emitting warnings or getting any kind of log out of the constexpr?
No. The committee usually doesn't, we usually don't standardize that kind of stuff, right? This is going to be implementation dependent. So your compiler is probably going to, try to be helpful there, but it's not the kind of stuff that we write proposals for.